So the goal of this tutorial is to build a scale, mini scale. I used to, yeah.
Oh, okay.
Um, so the material, the sensor is called strain gauge. It's a film resistor. It's just a very fine wires being printed on a plastic film. And when you bend it slightly or gently, it's going to change the resistance of the film. You can measure the change of the resistance from the two terminals. I bought both the, the strain gauges, just the films, the film resistors, and also I also have a lot of the strain gauges being mounted on a rigid mount, which is called a load cell. It's a metal piece that you can mount it onto the load cell. Before I tested it, probably 2 years ago, I didn't know that the load cell is super important to build a scale, and I was trying to measure the resistance change from the two terminals. So what I got is it's saturate the. Let me see, what did I do over there? I forgot if I used a digital meter to input the voltage change of the resistors into the analog input of the Arduino, or I directly measure the resistance change of the strain gauge. I think I used the ADC because the resistance changes of the strain gauges are super tiny. You couldn't actually read it from the multimeter. I was trying to read it. I think I damaged a few of them because I was trying to see some visible resistance changes from the film. It's not working at all. So you need a really sensitive ADC to measure the resistance change. And if you look at the sensor we are going to use, which is this board, it has a like 14-bit. Let's take a look at it. What's the resolution of the ADC? 24-bit ADC. It's extremely sensitive. If you just directly connect, for example, directly connect a film, if you build a voltage divider using two strain gauges and output the voltage to that ADC, if you don't use a load cell, which is a metal piece that you can mount to it, it's a rigid material, okay? You just use your hand to, even though you're thinking, you gently bend it a little bit, what's going to happen to the ADC? It saturates the ADC immediately. You couldn't even see the minor changes because any small change you put onto the strain gauge by your hand is huge. It's a huge change to the strain gauge, but it's not changing the resistance too much. However, that resistance change is going to trigger the ADC. It's going to give the ADC a lot of analog input and saturate the output of the ADC because your hand is still giving too much change to the strain gauge. Does that make sense? So that's why you need a rigid mount for the strain gauge. And I'm going to give every one of you 4 of the load cells. And actually, whenever you are, so first you mount the strain gauge, the film, to the metal, the load cell, and you are trying to press the load cell to see if you have any changes. And you couldn't even visually tell if there's any, if it's getting moving or there's any displacement of the metal, the load cell at all. You couldn't even see it. However, it's already sending a lot of signal to the ADC. Okay, that's why you need a load cell, because whenever it's giving a lot of pressure, it's not changing the resistance a lot. So it's taking the pressure, it's actually handling the pressure by the loading cell instead of the strain gauge directly. That's why someone can step onto the scale in the bathroom, right? But never the load cell. The load cell is just a thin film. Okay, you have to mount it to a load cell. And there are different types of load cells like this or this. Whenever it's getting bent, it's actually only changing the metal. Think about that. If I give you a metal stick, you try to bend it, can you visually tell it's getting bent at all? No, right? But if you mount a plastic film to the metal stick, actually that metal film, which is the plastic film, which is the strain gauge, will sense that little tiny change of the metal stick and translate into the resistance change of the strain gauge and being sent to the super sensitive ADC and being digitized, become a signal, okay? So these are all just low cells, just a metal piece, okay? And you can mount it to the locations that you should mount the strain gauge to. So this is different. Have you heard about, what's that called? You know, so this low cell is the one we have in the lab, right? If you look at it, it's a metal ring here, and it has a connection with a metal plate, just one connection, okay? And the strain gauge is mounted. I actually use a silicone glue. It's being mounted onto the metal plate in the middle. So keep in mind, there's no connection, okay? This is the only connection between this metal plate and the metal ring here. So you can imagine if you apply pressure, so the middle of the metal plate is a little bit higher than the ring. If you apply a little pressure on this, if for example you place this load cell onto the table, onto the flat surface, so the metal ring is gonna sit on the surface of the table, okay? But you have something in the middle. That's, for example, this is the metal plate, okay? And if you apply a pressure, it's gonna bend it, right? And that's gonna translate the change, the displacement to the strain gauge as a weight signal. So we have a lot of these ones, and you should use these sensors and this ADC in the lab and build it's called Wheatstone bridge. I'm gonna show the calculation of it in a bit. And you are going to build something like this and connect it to the sensor. So if you look at all the peripherals of this chip, so this chip is a IC chip on the module, which is this IC module here. We are not designing, putting all the required peripherals shown in this figure onto the board or breadboard, because the module we bought already has everything on it, like the caps, the resistors, and whatever the transistors. So everything's already on it. We just directly connect the digital signal to it and power it up, and feed the signal into the microcontroller. Okay, it's pretty simple. The connection shouldn't be that difficult. And I was trying to find out the internal connection of the low cell. So that's one low cell. It has 3 wires, a white wire, a red wire in the middle, and black wire. So what's inside is 2 1K resistors. So the 1K resistors, they are not just the 1K resistors, they are strain gauges, film resistors. The one low cell has 2 strain gauges, gauge resistors already in there, and has 3 connections, 3 wires with different colors, okay? And I was looking at one of the tutorials online, and they recommended the connections. Like, I'm going to draw a figure on the paper so you know why they connect everything this way. It's exactly a Wheatstone bridge that we are going to cover in a bit. Okay. So the goal is to build a minute scale. You don't want to build the big one that the person can step onto it. It's too big, too bulky. I just want to build a little tiny one with acrylic board we have in the lab. You can cut it in small pieces, probably this big, okay? And with the 4 low cells at the 4 corners, so in the future we can sell it to the K-12 kids that they can build it in their house and put their stuff onto the scale and look at the display. So that's the first, that's the main goal of it. And the details, the technical specs of it is we want a ESP32 as a microcontroller, and you have a PCB of the ESP32 for the scale, right? For the measurement. and send the signal out to another ESP32 wirelessly, Bluetooth, I believe, right? And display that on a LCD module. So you are not directly displaying that on the scale because the scale is too small, right? We don't want to put too many things on it. But we have another little PCB device wirelessly connected to the ESP32 on the scale. So a different PCB that you can handheld, put in your hand and see the numbers on the LCD display. So that's task number 2, right? So task number 1 is to build a mini scale with 4 load cells, and it's just a proof of concept. Read the data into a serial monitor. Okay, and 3D print the mount for each load cell. So the mount looks like it's just a little cover to place this to host this load cell, and have probably the holes for screws that it can mount to the board at the 4 corners, because there's no way that it can screw this onto the board, right? There's no place to do that. So I have to place this into a little 3D printed container, and with 4 holes at 4 corners, so you can mount it to the board. I think there are a lot of examples online and directly use it. I don't mind. Don't try to create everything by yourself. I just want to get this product done and make it work. Okay, you can find code from other people's script from last semester, from last year, whoever you think had functioning code. Just use it. You have to copy and paste because it's very simple. Just use it. And anyone posted code online, just use it. I don't care. I just want the product to be functioning, to be done by the end of the 3rd week. Let's take a look at it. So task number 1 is just to build a scale, right? And send the signal through the serial monitor so you can look at it on your computer, okay? And task number 2 is for wireless communication. Send a signal wirelessly to another board. For proof of concept or for task 2, you don't really have to get a PCB out of it. For task 2, it's just demonstrating that you can send it wirelessly. So have one breadboard measuring everything and another breadboard receiving the signal and display on the LCD display. You can use the bulky LCD display we have in the lab, or you can use a OLED display, the little ones. I don't really care as long as it works. Okay. I have a tutorial, just copy and paste in the microcontroller class. Recap on that really quick. So if you go to spring semester, you can find the ESP32 advanced IoT devices. I got part 1 and part 2. So I used ESP32 to sense the data to receive the data from the MPU 6050, the accelerometer, through I2C, and send it wirelessly to another ESP32. And there are a lot of details about how to do that. It's very simple. So again, copy and paste. Okay, don't try to spend like 4 days just for the wireless communication. Whatever is available for you guys, just get it done. Okay. Okay, let's take a look. Any other things I should talk about? So we are developing a product, instead of just submitting an assignment. So that's why you just consider yourself as an employee of the company. Try to get the product done as fast as possible. You are not trying to DIY every single script. It takes a few days for each step. Okay. The last one is design the PCB. I will send it out for fabrication again this time for PCBs. Okay. So this semester, this specific tutorial will take longer than last year because we are making a product instead of just building a skill on the breadboard, which is super boring and we're not gaining anything. So definitely after this project, working with you guys, I think at least we got a prototype, a little mini scale kit that we can maybe build really quickly, maybe just buy high schoolers and sell it later. Okay, so this one is due, the PCB files and all the report, okay, is due in 2 weeks. So I have 2 weeks to work on it. The PCB should be pretty straightforward. Like what I said, just use whatever is available to you guys. Online code, the code on my website, help from peers, just don't mind. Just ask for more help. Okay.
So for the PCB, you don't have to have the Bluetooth, right? It's just Bluetooth is just for that.
No, it's gonna be Bluetooth. The PCB is gonna be Bluetooth.
I don't get why we need Bluetooth for the PCB, right? If you want to make a product scale, it might be one.
Yeah.
It's just on the skill. That's right. It's actually,
pretty little scale.
yeah.
I'm thinking of this thing, I could use this at home to like measure out.
That's right. Yeah.
But if you have Bluetooth, you got two different PCBs.
Two ESPs on one board, right?
Yeah.
Because like I was finding using these ESPs on
That's right.
connections. So, like,
I think for the,
It's making it more expensive actually,
yeah,
increasing the cost.
So it makes more sense to just have it on one board instead of separate two boards that communicate
through phone,
That's right.
we have an app.
You don't really done the app. Takes forever.
Bluetooth real, Bluetooth scale.
If we don't use ESP32, if we just use the simple surface mount Arduino chip, right? Then we can build a very simple scale really quickly and with the lowest cost. The ESP32 chips still cost like $6-7 for each, but Arduino is only like 50 cents. That makes sense actually.
any microcontroller.
Have to consider profit.
Yeah, so let's use a cheaper.
Cheaper chip,
Yeah,
more profit.
use the 32 pin half mega.
Yeah. Yeah, let's do it. I think that makes more sense. If we don't use wireless communication and we just make it as simple as possible, right?
Yeah.
It will be a smaller PCB and everyone, you're not going to take a lot of time to solder it. So teenagers are not that patient to solder a big board.
Well, it's gonna be difficult to solder a chip no matter what.
Yeah.
What's more expensive now?
What? Oh yeah.
That's true. That's true. Yeah.
Why is it so much expensive?
Yeah, that's true. It's cheaper and easier to solder than as a product.
No way. Oh wait, no, they totally do it. Yeah, and then you can plug it in. Oh, it's totally possible.
But in that case, yeah, that's a good point. I think we should do that. And what about the PCB of this board? I don't want to buy it in the future. If we remove the task of the wireless communication, can we put whatever on the, I'm pretty sure you can find a schematic of it. It's super simple. It's just like how many components on it. Easy, right? Can we do that? Yeah, it's just ADC. Very sensitive ADC. And if you look at the traces they're not that complicated as well. I think you can, let's search for that. I'm pretty sure you can find a schematic directly because check some. Yeah, there are a lot of schematics of it. So yeah, you can definitely. So I'm pretty sure this PNP, this BJT here is a little IC on the chip, the little 3-pin stuff. It's a little thing, right? Yeah, the BJT, and it already shows the caps and resistors. Oh my god, this is super simple. You guys can get it done in like 30 minutes. I'm sure. Yeah. Just this is not challenging. And another thing I'm thinking about, I probably need your help. If you look at the wiring of all the load cells, it's very tedious and all the wires are tangled. Is there a way that we can design a way that they can wire it up easily instead of twisting the wires and soldering them? Strip the wire first and then twist it and then solder it. Let me show you how that was connected. The wires are pretty thin, very thin wires.
For the past, it seems like the resistance of our
not really. It's just a lot of wires. If you look at this tutorial here.
I have bought these 50-kilogram bathroom scale load cells and
See, like this.
Oh, wow.
Right? It's just a lot of wiring. Make it less fun. And I did it actually for my skill in the bathroom. I look at no, they wired it up. I forgot actually. They probably used the PCB. No, I mean we don't have to care about the products, right? Or the commercial ones. We just want to build one that for kids. They are handling the wires instead of
for the kid to set up.
yeah. It's not just a skill for them to use and measure things, right? They build it and then measure it, yeah, and solder the chips to the board.
I guess you should make it like instead of like soldering it to the board, you just have to plug it into the board that way. I mean, that's the only way I could see making stuff work.
Yeah.
Yeah, what are those cool comments? It's like small and white. Oh, yeah, yeah. Those are good.
Okay.
Like there's a so you plug them into a connector.
Oh, that's right. The one with a screw on the top. What about that one?
Oh, the terminal screws?
Yeah, the screw terminals. You gotta expose the metal core first, and then plug in and then screw it down. That's less important though. I'm pretty sure there will be a way to do that. But did you see this container, this holder here? Okay, you need to place that cell into the container. So I have to 3D print it. So I saw this guy directly download it from a website. So you can use it if you want. Just directly use it, right? If you don't want to. What's the weight? Yeah. It can be a wood board, can be, it's designed for someone to step onto it. So it must be a pretty. Probably has to be a thicker board. Will that be too? I mean, if we use 4 load cells, I'm not sure if it's for a heavy load on the top, like someone have to step on the board heavier than like 20 pounds at least to show a digit on it. If they build a small one, they probably don't have a heavy thing on the table to show a significant number on the display. It's probably not sensitive enough. Who knows? I don't know. I mean, 1 pound, 2 pounds, or a few grams. I have no idea. We have to try it first, right? See if we can change it later. Now, before we go to the lab to build it, let's look at the theory behind the load cells. It's called, looking at the name, Wheatstone Bridge. It's a sensor to sense resistance changes. And this is how you build that bridge. It's 4 resistors being connected this way. And you apply a voltage across these 2 terminals. It's called a V excitation. It's excitation voltage. And that's the 2 terminals you measure. You measure delta V here as the output. We label this as V1, this as V2, R, that's a constant resistor, R plus delta R, that's a change to the resistor. So for this type of Wheatstone bridge, it's called a quarter bridge, because only one strain gauge is put into the bridge. So all these ones are constant resistors. Just the one variable. So delta V, which is the output, equals V2 minus V1. According to the voltage divider theory, right? V2, if you look at this voltage divider, V2 equals V excitation times R plus delta R over R plus delta R. Is that correct? Okay. And V1 equals V excitation, just a half, because the 2 equal resistors. A lot of times because this bridge is super sensitive, so a lot of times a quarter bridge is not recommended. It's very difficult to find accurate resistors. You think it's 1K, but if you look at the data sheet, it's one of the color band shows like 10% plus minus. So you are actually you don't know if it's 1K or not. So if you have to use a quarter bridge, it's highly recommended to use 1 plus minus 1%. So a lot of precise resistors that you should use for the bridge instead of the raw resistors in the lab. Okay, and this equals VEX excitation so this is 2R plus delta R. Let's just use 2R plus delta R. It becomes 2R plus 2 delta R minus minus 2R plus delta R. Is that correct? So this becomes this 4R plus 2 delta R, and the top canceled. This becomes 1 delta R. Okay. So at the very beginning of the class, I told you guys that delta R is tiny, especially if you mount it to the rigid low cell material. The change here will be tiny. So you can actually ignore it. If you compare to R, you can ignore it. So this becomes V excitation 4R over delta R. So that's the output. Okay. If there's a change over R, which is this delta R, if there's a change, it has to be divided by 4R. Just making the change even smaller. Is that more sensitive or less sensitive? If you have to divide it by 4R, divided by a big resistor, is it making it more sensitive or less sensitive? No, it's less sensitive because if there's a little delta R, you have to divide it by a big resistor. So the change will be smaller. Right? And then let's look at the half bridge. If we see half bridge, top one. If this one is R minus delta R and this is R plus delta R, because these two string gauges are mounted on the different surfaces of the metal, the low cell. For example, you mount one here, right? And you mount one here. So if you bend it in one direction like this way, for example, you bend it that way. So these two string gauges are being deformed in a different way. So one is adding a resistor, one is minus a resistance. It's reducing the resistance, one is increasing the resistance because one is being squeezed, one is being stretched. So R, V1, V2, excitation, ground. Now let's derive delta V here equals V2 minus V1, which is Vx can be factored out. So let's just take it out for now. Okay. So it's Vx times V2. V2 becomes R plus delta R over this plus this. So delta R will be canceled. So we got 2R left. Minus here, which is still half. Right? So this becomes Vx times 2R, R plus delta R minus what? R. Okay. So compared to the quarter bridge, this is called half bridge. Which one is more sensitive? Comparing the half bridge is more sensitive because whenever you get a change of R on the string gauge, it's dividing a smaller number here, so it's getting a bigger change or bigger delta V. Okay? Yeah, so we'll do a full bridge. So the one we are using the full bridge. Let's look at the full bridge. Full bridge schematic. R plus delta R, R minus delta R, R minus delta R, R plus delta R. And that's V1, that's V2, and that's delta V. So delta V equals V2 minus V1, which is excitation Right. This becomes okay. So this is even more sensitive than the half bridge, right? Okay, now let's look at the schematic we are going to build on the board. So are seeing 4. So it's definitely a full bridge. Okay, because everyone is changing the resistance. Now, I was looking at the sources online, see what the schematic looks like in the low cell, and I found this from the video in the tutorial. It seems like we have 2 1K resistors in one low cell. If you have 4 low cells, it's giving you like 8 resistors. How that works? So I was looking at the connections from the tutorial, and I just drew the connections on the paper. Then it starts making a lot of sense. But now for this one low cell, for example, okay, it's nothing but just the 2 1K resistors with 3 wires, right? Okay, and now I found a connection diagram online. So you probably want to connect it this way. So the 4 low cells, I'll just simply draw 4 of them and then make the connections later. Okay. Okay, no problem here. So it just has 2, seems like these 2 terminals are equivalent. And the middle one is the output, so it's different. So if you look at the connections here, if the 2 terminals on the 2 sides are equivalent, which means these are interchangeable, because these four connections are nothing but just for these 4, like 1, 2, 3, 4. Okay, it's all the 4 sides. If you rotate it, it's going to be the same structure, so it's symmetric, and it doesn't really matter, I think. But you can try it and see if that works. Okay, but let's draw the schematic. Just looking at this one. We don't have to worry about these connections yet. Okay, 4 low cells. You see that the 2 low cells in the same row on the top, right? They have 2 terminals shorted together. Okay, and same for the bottom 2. And then the other terminal is shorted to the one below it. Okay, and the middle wires are all being used as a output or power line or ground or output for the module, the ADC module. Okay, if you come back to this drawing here, seems like you have to connect this 2, right? Or I'm gonna just do this. There's no difference on that. Okay, and then do this. Okay, and these are outputs. Outputs of what? So these 4 terminals are going to be these terminals. Either connect to power supply or the voltage output or ground are these 4. You can determine which one should be connected to where. But now let's look at the connections for these ones. Are these forming a full bridge? Like what I drew here? Is it a full bridge? Hmm?
Top would just be a combination of the, oh wait, no, because then you have the middle.
Can we consider these 2, because that's a wire, right?
Yeah.
Can we consider these 2 resistors as 1?
Yeah.
Okay, then it becomes a full bridge. Is that correct? It's just 4. Wait.
No.
You have to consider this become one. Hey, wait. Hmm. Oh, these two, right? Yeah, that's right. So these two is one resistor, and these two is one resistor. So you have 1, 2, 3, 4 resistors, and each one is each one is what? Huh? Come on, each one is what? You got four resistors in the bridge, right? Each resistor is what value? What resistance? That 2K? Yeah, because one is 1K, so we got 2 in for each. So basically, so you see one resistor is 1K, right? If you group 2 of them together, it's 2K. So it's 2K. It's basically a 2K string gauge. We got 2 string gauges in one group, which is fine. I mean, just making, so it's just every time you start trying to measure something, you have to tire it. So you have to press tire in order to calibrate the weight to 0, right? Because all the string gauges may have a little bit of output. If it's getting deformed a little bit, stretched or squeezed a little bit, under the loci, it may output a change. It's super sensitive. Keep in mind. So that's why you may read a little output can be negative, can be positive on the display. So you have to calibrate it to treat that as a 0 and start with that situation before you put anything on the scale, right? Make sense? Any questions? The code is provided. How to calibrate it, how to measure it, how to output the signal, it's just all provided. So you guys are making a product instead of developing the code, okay? Yeah, he might through hole. Yeah.
Sure.
The LCD is cheap actually. Let's use the LCD. It's bigger panes. Has a male panes we can directly plug in, even though it's bulky. It's less than $1, I think, for each of these ones. Okay. You may need a push button, right? A few buttons. So you need a debounce. So buttons can be on and off. You don't want to keep the display on all the time. It has to be battery charged, right? So in the terminals for the battery, you need the regulators. Consider using that 9 volts battery. There's 2 terminals on the top because it's slightly smaller than 2 cells, 2 AA battery cells, I think. So you need a battery, terminals, you need a regulator. I think the 1 amp is going to be able to do the job. So, and it's also smaller and cheaper. You need a button to turn it on and off. If you push it, it should totally shut it down, okay? You shouldn't display anything to save the battery.
Like zero function.
Zero function, right? Just 2 buttons should be fine, I think. On, off, and 0. That's it. We're not making it fancy, just make it cheap and work and make it work. Good. And the board on the top, if you are designing a die-stop scale, so I think the acrylic board works perfectly. It's clear, you can see through. It's really cool instead of using anything else, right? Yeah. Make sense? All right. Okay, let's do it.